Yesterday, I didn't call it this at any point. What we did was solve 2x2 systems of equations. What do we mean by 2x2 systems of equations and 3x3 systems of equations? What do you think that means? 2x2 means two equations with two variables. 3x3 equations or systems of equations are going to be three equations with three variables. Now, what are we dealing with here? If we're talking about three equations with three variables, here's what the first example is going to look like. Three equations with three variables. Don't write it down yet because I want to talk to you a little bit about what this means. What are we talking about? A 2x2 system, we said yesterday, was two lines that intersect in a point in the coordinate plane, right? So what we're looking for is an intersection point. What are we dealing with when we're talking about a 3x3 system of equations? Any ideas? Any guesses? No? Emily, did you have a guess?
It's X, Y, Z is 1, 3,
X, Y, Z what now?
Like, you see how there's X, Y, and Z?
Yes.
Three different variables.
Right, three different variables,
And then there's
three different equations, but what is the mathematical application of it? We can use matrices. We could set this up as a matrix and use matrices. You probably did that in Algebra 2. You probably used Kramer's rule to solve this in Algebra 2. One of the techniques. You might have used Gaussian elimination with matrices. That's another method. We're just going to use algebraic elimination today. But what we're dealing with here is three lines still. Okay, these are three lines in a three-dimensional space. Okay, there's an x-axis, a y-axis, and then a z-axis. Okay, and I'm going to do a very poor job of drawing this, but I want you to kind of imagine that we have still an x-axis, and it's kind of on a slant here. If you slant things, it's kind of easier to see the three-dimensionality of it. We have a y-axis. And then right through the middle, we have a z-axis. It's a vertical axis. Okay, so you can kind of see the three-dimensionality of that, I hope. But we could go, right to up or to the y-axis, right 3 and up 2, and then we could come up here. 4, and then we have this point that's kind of out here in space somewhere that lines up with the three axes. Okay, so we have a three-dimensional line. We have a three-dimensional space. It's a box, right? The box has three dimensions. So if I could take these three rulers, and I'm going to need a third hand here. I've got an x-axis and a y-axis, my normal x-y axis, and I'm going to add z to it. Hold the z-axis for me there, right? So I've got a three-dimensional space. And so I can go right, left, and up. And so I've got a point that's hanging out somewhere in here. And these equations that we're looking at define lines in this three-dimensional space. So I might have this three-dimensional space, and I've got this line kind of sitting out here in 3 dimensions. That's what these lines look like. All right, now I want you to kind of think about the lines in three-dimensional space. So if this room is a three-dimensional space, and we have these just kind of random lines out here in space, there's a lot of ways they cannot intersect, aren't there? Like these two lines are not going to intersect. Right? As a matter of fact, if we just threw these things into like a gel and they hang suspended in three-dimensional space, getting two that would cross, probably not likely. Getting three that would all cross in the same point would be, theoretically impossible that you could randomly do that. So when we generate these problems, these lines in three-dimensional space that all intersect in a nice little point, it's kind of fairy tale land. But it works. All right, so these are lines. We're still dealing with linear equations, but we're dealing with linear equations in a three-dimensional space. I think I mentioned to you yesterday linear algebra. the college course that's kind of one of the lower level college math classes that you can take deals with a lot of matrices, and you actually do some 3D graphing, and you kind of look at some things like this in space so you can see what they're doing. There's a lot of applications to multiple variables, equations with multiple variables, right? Can y'all think of one? Anybody here own a business? Anybody here family own a business? What's your family business?
Environmental contractors.
Environmental contractors. So they have different services, different products, right? What about yours? Insulation. So you would have different products and different services involved. I need some insulation, but that's off the subject. If we've got 3 different products in a business or 5 different products in a business, those 5 things represent 5 different variables. Okay? And so you have multivariable situations in real life, a whole lot more common than just 2 variable situations. You know, we're used to in algebra just dealing with 2 variable situations, but real life there's multivariable situations. In a business you might sell 5 different products or 10 different products or 15 different products. And each one of those products represents a variable. How many are we going to sell? What's the price of them? How can we maximize profit? All those things come into play in those multivariables. The math kind of comes into it. So 3-dimensional stuff is really cool. I hope you guys, some of you will take that linear algebra course in college and get some exposure to it. See the look of excitement in your eyes. All right, so how would we do this? Y'all remember? What's your recollection of this from Algebra 2, other than hatred? As Daniel's about to say something like death or hatred or
If you were there, you'd understand.
hell and the devil, something like that.
If you were there,
That's what I remember. Yes.
Don't you make the first equation equal to x or y, and then the second equation equal to z, and then plug both of those into the last equation? Is that not how you do that?
That would be kind of a substitution method. You could work some substitutions out and probably do this, but that would be a little bit more complicated than what we're going to do today with elimination. But there's some substitution methods that you can do with certain systems of 3x3s that will work. I think it's probably a little bit difficult with this one. The goal here is to start off by eliminating one of the variables twice.
When you just, instead of working all 3 at the same time, you work with 2 of the equations first.
2, we're going to pair them up. So what we're going to do is pair up. Do y'all see a variable here that would be really easy to eliminate? Z. Go ahead and write it down if you haven't written it down. I'm sorry, I told you not to write it earlier. And I want you to write it now. Z would be really easy to eliminate, right? And what I encourage you guys to do is when you write these down, number the equations so we know what we're dealing with. So we can talk about them. Equation 1, equation 2, equation 3. So what I would do first here is look for a variable that's really easy to eliminate. The z is really easy to eliminate if I add equation 1 and equation 2. Right? So let's add equation 1 and equation 2 and see what we get. 1 plus 2. So I'm kind of listing what I'm doing here. What is 1 plus 2 going to give us? 3x plus 4y. The z's cancel equals 11. I'm just going to put a box around that and save it for later. Okay? Now, once you eliminate one variable, we're kind of stuck with eliminating that variable. We need to pick 2 different equations and eliminate the same variable again. All right? So let's pick which equations you want to use to eliminate z.
The middle and bottom.
Equation 2 and equation 3, how would we do that? Multiply equation 2 by 2. And that'll give us, we'll kind of come down here below. No, I'll come off to the side. That'll give us 4x plus 6y minus 2z equals 10. And then equation 3 is 3x minus 4y plus 2z equals 1. So what we're doing here is using two different equations to eliminate the same variable. Two different pairs of equations to eliminate the same variable. All right, now I'm going to eliminate z, and I'm going to be left with 7x plus 2y equals 11, because the z's will cancel. All right? And we'll put a box around that one. Now that we have eliminated that variable twice, now I'm left with these two equations that I can work with, right? 3x plus 4y equals 11. 7x plus 2y equals 11. And now we're back to doing what we did in class yesterday. 3x plus 4y equals 11. 7x plus 2y equals 11. And you guys can just kind of come down below on your paper and write those two together. Now, we've got a lot of different ways that we can use to solve this system of equations, right? Suggestions. What do we need to do?
Multiply the bottom by negative.
Multiply the bottom by negative 2. That's correct, Bryce. And that will carry us over to 3x plus 4y equals 11. Negative 14x minus 4y equals negative 22. Now, I noticed yesterday, or I noticed in your homework when I was checking your homework from yesterday, that a lot of your form was really, really sloppy. I was seeing a lot of processes that you were doing mentally that you're not showing. If you try to do that with these 3x3 systems, you're just going to get lost. You really need to have good workflow so you can kind of see where everything's coming from, where it's going to, what you're doing. Show the steps so you can double check your work. One little careless mistake along the way and you miss the problem. So you got to be really meticulous. 4y minus 4y is gone, and we have negative 11x equals negative 11, which means x equals 1. And we've finally gotten a numerical value that we can work with. Okay, now what will we do with that x equals 1? Plug it back into one of these two equations that we're working with. Let's use the first one. 3 times x plus 4 times y equals 11. And then we can subtract 3 from both sides and divide by 4, and we get y equals 4. 2. Thank you. I don't know where 4 came from. See what happens when you skip steps? Just telling you guys not to do. You get 4y equals 8, which means y equals 2. All right, now we know an x value. We know a y value. What do we have to find still? The z value. So I need to go back to one of my original equations. Let's use that first one, which was x plus y plus z equals 6. Right? Equation 1. And then that will give us 1 plus 2 plus z equals 6. And that's going to result in z equaling 3. All right, so our ordered triple, this point of intersection in this three-dimensional space, is 1, 2, 3. Okay. 1, 2, and 3. All right, any questions there? Everybody good with this? It's not fun, I know. It's like a big puzzle. Okay, so let's kind of look at the steps again all together here. If we take the two equations and add them together, we eliminate the z and get the 3x plus 4y. We need to eliminate z again, so we use the next two equations, multiply. This one does it a little differently maybe. No, that's what we did. And then you add those two together and you get 7x plus 2y equals 11. And now we have a 2 by 2 system that we can solve. We solve that 2 by 2 system, we get x equals 1, substitute that into one of the original equations, and we get y equals 2. And then we can substitute those two values into one of the original equations, x plus y plus z equals 6, and we get z equals 3. All right? Example 2. Give you a second to write it down. 2x plus y plus 3z equals 8. X plus 3y minus z equals negative 6. And 3x minus y plus 2z equals 2. So let's identify our equations so we can kind of talk intelligently. Equation 1, equation 2, equation 3. All right, now step number 1 is to eliminate one of the variables. Do you see a variable that is easy to eliminate? The y's are the easiest variable to eliminate. Now, it doesn't matter which one you eliminate. You could eliminate the x's, you could eliminate the z's, but if you go with something that requires no multiplication, you're going to save yourself a little bit of time, usually. So we can add equation 1 and equation 3, right? If we add equation 1 and equation 3, the result is 5x plus 5z equals 10. No, you're welcome to continue with x if you wanted to. You're going to get there. It's just, a different process. You're going to get the same answer. As long as you don't mess up. Now, if we eliminate y once, we need to eliminate y again using two different equations, right? But we're going to save 5x plus 5z equals 10. We're going to save that, put a box around it so you can find it in your workflow, and that's one of the equations we're going to use as a 2 by 2. All right, we got to eliminate y again. Let's use equation 2 and 3. How about that? What would we do to eliminate there? Multiply the second, or equation 3 by what? If we're eliminating y, we need to multiply it by 3. Right? And so that's going to give us x plus 3y minus z equals negative 6. And then the third equation is 9x minus 3y plus 6z equals 6. Sorry for the chicken scratch there. When you add those together, you get 10x. The y's will eliminate, which is what we want. Negative z plus 6z is 5z. And negative 6 plus 6 is 0, the hero. Right, so our second equation is 10x plus 5z equals 0. So that's the two equations that we're going to use to find x and z using elimination most likely, because elimination is just kind of the most friendly method to use for solving systems of equations unless it's just really set up to use substitution. All right, so the two equations we're going to work with are these two. Now, what are we going to eliminate? What's easiest to eliminate from here? Z, right? So we can change all the signs. We're going to eliminate z, and that's going to give us negative 5x equals 10, or if you change the other one, you'd get 5x equals negative 10. Either way, you get x equals -2 as your solution for x. That's one of our variables. So in this three-dimensional space, we're going to the left 2 or to the negative side of the x-axis. There's not really kind of have two lefts and rights on the x and y z axis. There's 6 directions. So. All right, now what would we do with that -2? Plug it into one of these equations. Take the first one, 5 times -2 plus 5z equals 10. Add 10 to both sides, we get 5z equals 20 and z equals 4. All right. Is everybody okay? Y'all ahead of me? X equals -2, z equals 4. So now we need to go all the way back to one of our original equations and plug in x equals -2, z equals 4. Now, you need to be really, really careful here, right? What could you do wrong here if you're not careful? You could make a substitution for the wrong variable. You could just kind of, x and y. We're used to working with x and y, so if you put the -4 or the 4 value in the place of y instead of z, then you messed up. Okay, so make sure that you are making the right substitution. Y equals 0, and likewise, when you put it into your ordered triple, it has to be in the correct order. So x is 2, -2, y is 0, and z is 4. I see sometimes students will take this and do a problem like this and work it correctly and then put the answers in the wrong order. An ordered pair is ordered alphabetically. It's not ordered numerically from size. This is smallest to largest numerically as well, but it's not. It's ordered alphabetically. So if the system of equations had A, B, and C in it instead of X, Y, and Z, then you're going to have the A value first, the B value second, the C value third. Always ordered alphabetically. All right. Try this one on your own. Try this next example on your own. We're nearly done. So our final answer is going to be 3, -1, and 1/2. Okay? How many of you got that correct? Most of you. That's good. That's good. Okay? All right. Let me show you one example that is a little bit out of the ordinary. We're not going to have time to write this all down, so just kind of pay attention to this, and I'll walk you through it. What's different about this system of 3x3, this 3x3 system? What do you notice right off? Anybody notice anything right off? The x and the y are the same in the first two equations, which means we could multiply one of those equations by -1 and eliminate two variables at once, which is always a good thing. That's a gift, right? If we can eliminate two variables at once, we end up getting a direct solution for one of the variables. Z equals -4. Is that helpful? Yeah. Absolutely. Now, but what would you do with it?
No, I'll just keep it there.
Well, you could keep it there, but I would plug it back in. And here's why. You could take the second equation, plus 8, right? -2 times -4 equals 11. You could take the third equation, x plus 4y plus 3 times -4, that's -12, equals 11. All right, and then we can subtract 8 from both sides, get x plus y equals 3. The bottom equation, if you add 12 to both sides, you get x plus 4y equals 23. Did I mess up? Yeah, -6. Thank you, Charlie. I knew the 23 wasn't feeling right. Add 12 to both sides and you get 6. Right? So we can use this found numerical value and substitute it into two of the other equations, a combination of the other two. It can't be the same two, because you'll get an identity. All right? And you get an equation that's 2 by 2 that you can solve by elimination. Subtract it, and you're good. Okay? So if you can eliminate 2 variables at once, that's always a good thing. Go with it. All right, here's your homework. Oopsie, backsie. There you go. Make sure you can take a screen, take a picture of this. Make sure you get the answers in the solution as well in your shot.